Vortex rings form when a liquid or gas is pushed out of a hole. The initial friction from the hole slows the outside of the ring down, while the center of the ring proceeds to move at a faster velocity than the outside of the ring, causing the substance to curl in on itself. This causes the expansion of the ring as the substance keeps moving. The underwater vortex rings have more movability and longevity than those in the air, as the air rings dissipate much quicker. You can see this comparison in the video shown with the scuba diver blowing bubble rings and the smoke ring coming from an air cannon.
As you can see in the previous videos, when the liquid is forced through the apparatus, the fluid initially forms a spherical shape. This is due to the friction that the apparatus acts upon the fluid. Once the fluid is introduced to the surrounding environment, the friction between the two fluids causes the molecules on the outside to be dragged back, while the molecules on the inside speed up. This difference in speed causes a vortex, where the slow-moving fluid is sucked back into the center. The increased speed on the inside is caused by Bernoulli's principle for movement normal to a streamline. As shown in this equation, the fluids towards the center will move at a fast rate, and as a result, the increased speed will cause a decreased pressure and will increase the propulsion of the vortex.
In watching several videos about vortex rings, both underwater and in the air, we hypothesized that underwater rings are easier to form and are more stable due to water having a higher density and viscosity. Our rationale behind that theory was that since water is drastically more viscous than air, the vortex rings formed underwater have more structure and stability and therefore will sustain the ring shape longer. We noticed that the rings produced underwater were able to experience a force yet maintain the ring shape.
Although it was previously thought that the Reynolds number was the main criteria for vortex ring formation, recent studies have shown that the Ohmsorge number is what defines the ability of a vortex ring to form under the given parameters. As seen in this equation, the formation capability depends on fluid viscosity, density, surface tension between the two fluids, and the diameter of the initial drop or exit hole. Using this equation, it is evident that as the viscosity of the fluid increases, the Ohmsorge number increases, and as the density, diameter, and surface tension increases, the number decreases. The ideal value for formation is if the Ohmsorge number is greater than 0.011.
A higher Ohmsorge number shows that the ring is able to be formed more easily. So although a vortex ring may be more difficult to initially create underwater, it will sustain its shape for a longer distance/time. After observing several vortex rings, we developed the hypothesis that a vortex ring traveling through a fluid with a higher viscosity, like water, will be easier to form than one in a lower viscosity fluid, like air. After examining the Ohmsorge number and its relation to the vortex rings, we figured out that viscosity is not the determining factor of stability of the ring. The main factor influencing the rings is surface tension. This makes sense as water has a higher surface tension than air, which allows the ring to propagate for a longer time without breaking form.
From this analysis, we can conclude that, from looking at Bernoulli's equation, as the speed of the moving fluid increases, the pressure decreases, which is why the center of the ring moves faster. Our initial hypothesis was incorrect, and the formation of the ring was not dependent on the viscosity. Instead, it was more dependent on the surface tension of the water. This makes sense because the higher surface tension of water allows the ring to sustain longer than it would in the air.